So first I will introduce some main concepts that let's say we had in mind when we developed these softwares. And so what we wanted to do was to run QTL analysis in a germ plant that is wider than a biparental population. So that's why in the title you see multiparental population. In fact, it's not just restricted to multiparental, it can be a mix of some also with some unrelated material, let's say something more similar to a GWAS panel. So that's why I'm talking here about just something wider than biparental, so a structured, a structured population. And the other main concept is that okay, we wanted to use haplotypes, so ancestral alleles, let's say, instead of SNPs, or well, both of them. So to have the possibility to use biallelic SNP data and multi-allelic haplotype data if available. So that's why actually in the pipeline that we developed, there is this natural workflow in which first you need to get some genotypes, so possibly haplotypes, and for that, in this particular situation, we have developed this other software that is called Polyploids. Roland Wurips developed it, and actually tomorrow I think he will give a demonstration on Polyploids. So Polyploids is facing, let's say, is inferring some local haplotypes, and then these haplotypes can be used in mpQTL, which is actually just doing performing association analysis of phenotypes and genotypes. So today I will just focus on mpQTL, but bear in mind that let's say Polyploids was the other software that we had in mind and we developed together with it. Okay, so talking about the type of germ plots that we want to use for this analysis, as I said in the title, preferably connected population. So populations, F1 population that are sharing a parent, and that's why that's because this setting, let's say, is particularly is used by Polyploids to infer the haplotype. So when with this setting, let's say a Polyploids can make use of the genetics to improve the haplotype inference. But the mpQTL in itself is not limited or restricted to this type of population. In fact, you can have any structured population because the model will account for that. We will see how. So the only point is, as far as you can get some accurate haplotypes, then the mpQTL will just run the association analysis. And of course, in this situation, if you look at these two types of say relationships among individuals, so in this part here, Polyploids will be more accurate, because of the connections. So because it will take advantage of the connection, and here the haplotyping will be at a lower power, so less accurate. And the other concept we said is that the fact that we would like to use haplotypes in instead of biallelic SNPs. And so in these slides, I just would like to illustrate these concepts. So imagine in the bottom line here, you have the genetic effects. So imagine in this population, you have 5 different alleles, and actually there is just one functional allele. Those are the genetic effects. So there's one functional allele, and the other have identical genetic effect. So you need something that is describing as better as possible this variation. Of course, when you use SNP alleles, you're restricted to just 2 alleles. So in fact, you're grouping, right? Your effect into just 2 groups. In this case, for example, you're grouping the first 3 alleles and the last 2 alleles into these 2 groups. And of course, that's not ideal to have a good description of those genetic effects that are segregating in your population. So in multiparental population, you could decide to use every chromosome of the parents as a different as a different effect. But of course, they in that case they are a bit too many, in the sense that some of them can actually be identical. So that's also, it's perhaps an improvement, but it's not ideal as well. So what we want to aim is to have the third line, so the ancestral alleles, which are much more likely to describe very well the true genetic effects that are segregating in the population. And to do that, yeah, we let's say we need to infer these haplotypes. In this case, I'm talking about local haplotypes, so I don't need to have a really large segment of genomes of the genome to be, say, phased, but just the locus. Preferably in this locus, we shouldn't have, let's say, recombination, or the recombination should be at low, at a very low level. Okay, we can go to the next one. That's about the mpQTL package that we have developed. As I said, there are, let's say, 2 main steps. In the first steps, you want to get the genotypes, and in the second one, we run the association analysis, and mpQTL is actually doing that. So just the second part, just the QTL analysis. And the model that is using to do that it can correct for a population structure, let's say, both for population structure and for relatedness. We will now see it a little bit better in a next slide. One main point is that it's quite flexible, because it can get this kind of model, because it can accept biallelic or multiallelic markers, and you can have, in fact, any population structure at any ploid. So the main point is, or maybe the most difficult part in this pipeline, is to get really accurate genotypes. And ideal, yeah, this is what we want to use, the ancestral alleles, as we said. And to do that, yeah, we developed polyhaplotyper, especially for this situation with connected populations. But there are also other software. So for mpQTL, that's fine as far as then the format is accepted by the software. So we can even, let's say, instead of haplotyping, instead of inference of haplotypes, we can even use some more direct observation of haplotypes, for example, using amplicon sequencing or so as far as the format is, the input format is accepted, and yeah, any haplotyping software can be used. That will be the most informative type of genotypes that we could use for this analysis. But let's say if you go back in towards less informative types of genotypes, we said we could have parental alleles. So considering all the parental chromosomes as different alleles with different genetic effects, or we could still use biallelic SNP alleles. They could be both deterministic, so dosages, or probabilistics, and even continuous data actually are also accepted by the model. So if you have, for example, array intensities, and those ratios of intensities can be directly used as well. But of course, yeah, there is a loss of information if you go in this direction. So the ideal situation is the one in which you can really use the data and get accurate ancestral allele. So that was the aim that we had in mind. So mpQTL has been developed by Alejandro Teresa Navarro, that I think he's there with you, and myself. And now we will talk a little bit more about the package quite soon. So first, I would like just to introduce the model that that is implemented, and it's a model that is used also in GWAS analysis, and is also called unified mixed model. And it's a model in which the phenotype is it has this form, so the Y is the vector of phenotypes, and the beta vector and the V vector are fixed effects. We will see now what they are. And the underlined factor here is a random effect. So this is the U vector is a vector of random effect that is accounting for relatedness of among individuals. And the other two, so and the Q is actually the factor that is accounting for let's say a more distant type of structure. This could be, for example, a categorical variable if you have already some knowledge about clustering, or it could be a set of principal components, for example. Okay, so as I said, these are the two then factor that is together accounting for all the types of genetic structure that you can have, and the relatedness is structured based on a relatedness matrix that is based on the genotypes. So in the first factor here, in the beta vector, that's could be let's say a set of variables say that can explain part of the phenotypic variation, like some cofactor that you want to have, and then there is also the marker that we want to test, and we will see how it differs whether we want to just include a biallelic SNP or a multi-allelic marker. Okay, so that was the model, and now I would like to briefly to introduce a little bit about the input data. As I said, there could be several types of input data because the variable, the genotype variable, it could be in fact continuous. So like in the first case here, for example, using SNP intensities from a SNP array. So in this case, the input is very simple because you have SNPs in the rows and you have individuals in the columns, and this ratio is indicating the contribution of one allele to the total. Then these data usually, at least in this pipeline, are used to be analyzed to call the dosages. That's done by FitPoly. Well, there are also other software, but this is what we have developed in our department. And actually, FitPoly first is estimating a probability for having each. So the probability of having a certain dosage, a dosage of 0, dosage of 1, of 2 or 3 or 4. And then based on this probability is assigning a more deterministic dosage. For example, here for the SNP1 in the first row, so individual 1 and SNP1, you have probability of 0 for all the dosages except the probability of 1 for dosage 4. So then the dosage call will be 4. But in certain cases, you could, like in the second row, you cannot really assign, let's say, a dosage because here, for example, you have 40%, 0.4, probably 0.4 for dosage 0 and 0.6 for dosage 1. And then in this case, probably in the output, you will have a missing value because there's still an uncertainty in assigning it. So another possibility is to use directly the SNP dosage probabilities and transform them back to something continuous, like this table here below. That's pretty similar to the previous one, to the SNP array intensity, but there is more information there. So it's in fact probabilistic genotypes, but still a biallelic one. And then, as we said, we wanted also to use multi-allelic genotypes, and Polyploids that we used to do that, to infer the haplotypes, is producing an output that is of this form. So for each locus, so for each small haploblock concatenation of few SNPs, it will infer a number of haplotypes that are in the row, and it will assign the dosage of those haplotypes for each individual. So for example, here G1 is first individual, and it will have 2 dosages of this haplotype, probably 120, and 1 dosage of this haplotype here, 130, and 1 dosage of the haplotype 149. Those are formed because this is a tetraploid individual. So it's a kind of list in which each table is a summary of is reporting the dosage of each haplotype for each genotype. But actually, the table that is used as an input for mpQTL is the one below. It's just the same, but it's just let's say converted in this way. So here we have a locus for each row, and an individual is described by 4 columns, so 1 for each homolog, and for each column the haplotype name, let's say, is reported. So this is the example below, in which we so the example above, in which we have 2 dosages for G1 for 120, just 2, and 1 dosage of 130 and 149. So this is the actual inputs that is used, format input that is used. So to conclude the introduction, so this software actually being developed partly based or using a simulation study to prove the concept mainly, and this was published last year by Alejandro. This one is one figure of the paper, and just to show a comparison of QTL analysis using SNPs, where the dotted line here, vertical line, is a true QTL that we have simulated, and this compared with IBD data. So those are the true allele at any position in the genome, with haplotypes that are the true phasing of haploblocks, so of these small, let's say, concatenation of SNPs that we can use to infer them. And the idea is that with the allelic SNP, you have often a peak that is not very clear. The position, it could be not very clear. Perhaps the power of detection of the QTLs, it could be still good, but especially for the position of the QTL, you should have quite an improvement using multi-allelic data as haplotypes, as far as we can accurately detect them. Okay, so that was my last slide. So thanks to Alejandro. Alejandro, as I said, he did develop the mpQTL software together with myself, and he's there. So now we will in a few minutes we will hopefully start the software demonstration in case there is any need. Perhaps Alejandro can be there to help you. So thanks to the colleagues that have collaborated, contributed to this work, and all our colleagues that are working on Polyploids, which is actually quite a big topic nowadays. Okay, so I will then go to the demonstration part. Okay, you see that, okay, this is the, so you can follow maybe a bit the vignette, and because this is just the code that is included there with some more explanation there. So that's up to you. You can keep an eye here maybe. Okay, so what I'm doing, first I'm installing the package.
Giorgio, could you increase the size of the font, make it easier to see?
If I remember how to do that.
Go to view, and then from view, zoom in. So fourth, yeah.
Is that okay?
Yeah.
Perfect.
Thank you.
Okay, so I'm just loading some data, and the data that I will use in the demonstration is actually a set of simulated data set, and you can see that it contains several tables. There is a table of phenotypes, there is a map, there is a table with biallelic SNPs, and there is a table with haplotypes or founder alleles, let's say. Sarcofactors. Those are the results of let's say polyplotyper, and the map and the pedigree. So now we will a little bit go through this data. So the first, actually, in the first part, I will just try to show you what is needed for inferring the haplotypes with polyploids, but I will not go into the details because then this is covered by Burips tomorrow. So I will just briefly go to touch some of those information that are needed. The first thing you need is pedigree, and this table with this form with 3 columns, and here the name of an individual, and here the 2 parents, parent 1 and parent 2. So for each individual, you have the 2 parents specified. If there are no parents, means that those are founder individuals. So with this, I will get the parents. Then we can see all the parents in the population. So all the crosses, each of those combination is a cross of 2 parents. Then I will merge the reciprocal one, but actually I think it's the same in this case. And then I will build this list, which is a list indicating for each cross all the individuals in the progeny. So the first vector is the progeny, so the name of the individuals of the progeny of the first cross here. So this list that is defining the structure of the F1 families, or the list of all the F1 families. And then what you need is actually also to run polyhaplotyper. You need to define these haplo blocks, so these loci in which you want to phase you want to phase the SNPs. And so it means that you need some information on the position of the SNP markers, or at least on their proximity. So in this case, we actually just based our analysis on a map. Some of you maybe can recognize some marker names. Those are from a potato dataset. But that's not relevant here. So what we simulated, it's a set of 4 chromosomes, and in each chromosome here we have this number of markers in so about 600 for each chromosome, and that's the chromosome length. So 0 is not the chromosome actually; it's just something fake. So those are SNPs with no position, and they are put there in a chromosome that is called 0, and this length is just for visualization purposes, but that's not real. So those sort of information actually you need to run polyploid. We will not do that now. Instead, we will just use some results of polyploid. So this table is actually what polyploid will output. And first, maybe we can have a look at the first table. So it's just the results for one locus, and what it's saying is what is the dosage for each of those haplotypes in the row. So for this locus, the software inferred 21 different haplotypes, and for each individuals, it can give you the dosage of each of them. So the first individual here, it has 1 copy of haplotype 1, 1 copy of haplotype 2, 1 copy of 3, 1 copy of 4, and so on. So for the second one, we have 2 copies of 1, and 1 of 3, and 1 of 5, and that's it. So this is the a table for each locus of the dosage of each haplotype, and of course each of those columns should sum to 4, because those are all tetraploid individuals. Okay, so actually what we've seen that that's not the format that is accepted as input by mpQTL. So we are just now doing a conversion into the input that is accepted, and we use this function. So that's actually the conversion that is doing. So now we have a table in which for each locus we have the genotype of each individual that is described by 4 columns, a column for each homolog, and is telling you that each individual has 1 copy of haplotype 1 that is called 01, 1 copy of the haplotype that is called 02, and so on. So in this case here, you have 2 copies of 1, and 1 copy of 3, and 1 copy of 5. So this just the previous one is actually a list in which you have each element is this table for each locus, and this is just one table in which each row is describing the genotype of different locus. So now to run actually the the association, we need also a position for each marker. So for each multi-allelic marker in this case. So I will just calculate the mean or the midpoint of all the SNPs that are included in one of those in each of those loci, and so the final map for our haplotypes will have this form. There are 3 columns. The first column is just the locus name and the chromosome position, and the position on the map. So this position is just the average of the SNP markers that are used to, or that are phased, and let's say in this locus. But we will just save them for later, and then we will have a look at the other tables in the simulated data sets. So this is just a table of biallelic SNPs. So for each row you have a SNP marker and its dosage for each individual. That's something you are used to probably. Well, this is what we have just produced, which is the table of haplotypes, say haplotype names. Well, and of course you can let's say switch from one format to the other. That's just those are just some utility functions that are included in the package to convert to the input to the right format. Okay, so this basically was the let's say the genotyping part. So the part to format the input data, especially the genotypes. I just showed you what are the information that are needed, but then follow the workshop tomorrow, Roland Burips on the polyhaplotyper, because take in mind, have in mind that that's a part that actually will be in the workflow will be here, because then the results of the haplotypes will be actually used, can be used as input in mpQTL for the association analysis. Okay, let's see. As I said, so here there is not an we don't have an example, but so those are just those discrete dosages of SNPs, but biallelic markers, as we said in the introduction, can be also continuous. There is no problem to use continuous data for biallelic markers here as input in mpQTL. Okay, so that's just a recap of everything now. So this already we already seen. I will put everything here, and then we will have a look to these additional files now. So the haplotypes and the haplotype map is what we produced before, right? This is the haplotype table, and this is the haplotype map. The SNPs and and then this is a table of phenotypes, and that's what we need to run our association. In this case, we have 2 different phenotypes. for all the individuals of this data set. Well, I just checked here that they are the markers in the same order, and individuals in the same order also between phenotypes and SNPs and so on. Okay, so what first we will do is to calculate the relatedness between individuals, and that's it's needed for the correction of genetic structure. Now we have different options, and one option is just to actually to use a kind of membership to cluster if you already know in advance some clustering. That's the case for this simulated data set because we know how we have simulated them, but it could be also the case for some real data set. So this vector pop is actually assigning each individual to a cluster. So this A1 is one cluster, let's say. A2 is another cluster, A3 is another cluster. And those are actually the clusters from which we have extracted the parents of the population. And those are actually the families, so the crosses. So we have already structure and membership of individuals to this kind of structure. So we could just use this membership as a fixed effect in the model to correct for this structure. The other option is to calculate a relatedness matrix, and that is done by this function that is actually just doing a cross product of the genotype matrix with its transpose matrix. And we can do that for the SNPs, but we can use the same approach to calculate relatedness for haplotypes. We can visualize them, but I need to create a little bit more space here. We can visualize them. So that's the heat map of the dosage matrix. We have seen this kind of metrics also in the previous talk. So here you have all the individuals, and the color is according to the relatedness. So the darker, the more related are the individuals. You can see that there is these squares, let's say, that are representing the genetic structure of the population. But there is also some relatedness between different families, and that's because of the relatedness of the parents. So the heat map of the haplotype matrix is actually looking pretty similar. That's what was expected. Okay, and the other thing that we could do is to run a principal, in this case, principal coordinate analysis, and to plot it. That will be another option to be included in the model to account for structure. For the moment, we will calculate it, and then we will see how to use it. So that's just, in fact, is a calculation of the principal coordinate analysis of the coordinates and the plot of them. and you can see here how it looked like. Here we have used as color. We have used the membership that we already knew to the families. So those clusters are the families, the F1 families, and some of them are closer to each other. And that's pretty similar, I guess, if we do that on using the haplotype matrix. Actually, using the haplotype matrix, this clustering is a little bit more defined, but so that's not the point here at the moment. Okay, so this part was about, well, all the information that we could use for the correcting for the genetic structure, and now we will see how to use them. So first we have a look at the main function that we will use for run the association analysis in mpQTL is called map.qtl. We can have a look at the documentation. So here you can see a bit of what I've already seen. This is the main model that we have used, and you have the description of all the arguments. So we will see some example here, either not using any information for genetic structure correction, so which means that we are just using a linear model basically, including just the coefficients of the marker we want to test. So that's the first example here. But first, I want to show you just this other manual. That is actually the core function that is used within map.qtl, which is called solve, and that's the function that is solving this model. It's a function that is partly based on the mixed solve function of RRBAP developed by Endelman. So it's using the same approach basically. Although it's so that's a very nice function and very clearly written. I really like that. So this function is not identical. I think singularity perhaps is handled differently, and of course this is handling the multi-allelic markers. The parallelization is also somewhat different. So yeah, it's there are some. Let's say I cannot guarantee it's as good as the mixed solve function. So let's see the first example. So this is just an association of the phenotypes and the biallelic SNPs. And here we're not using any correction for population structure. This will be just linear model basically. It says no Q matrix will be used, so a linear model will be used, and it's also pretty fast. And this is let's say what how the output looks like. So you have for each phenotype you have basically 4 different things. So the beta, and then the results of the F-test, the p-value, and the standard errors. And so in this case, if we look at the betas, you can see that actually you have just they are just two. This is just the intercept, and then there is one beta coefficient for the marker that we have tested. So I will put here the p-value, and the sky plot is just plotting function within mpQTL that is to create the Manhattan plots. So this is how the Manhattan plot will look like for the first model. So the second model we will run, it's very similar, but we are now using the haplotypes instead of the SNPs, and the map is also according to that. This is also a linear model then. We are not correcting for a population structure. So it should be also really fast. That's it. Yeah, so the structure is identical actually. So if you look at the beta now, you have so still an intercept for each marker, of course. For each multi-allelic marker, you have still an intercept, and then you have a coefficient for each allele, for each haplotype. So I'll plot them as well. Here is pretty strange, the output. And that's because of the information that is carried by the haplotypes, and the fact that we are not correcting for population structure. So now we have the first example of correction. For population structure, we are using again the SNPs, and we are just correcting by including the model a vector of membership to clusters as a fixed effect. So here it says no imputation because in this simulated data set we do not have any missing value in the genotypes. So it's still using this linear model, but with a correction for now. If we look at the betas, and we see that we have still the intercept for, we have a beta for each cluster, population cluster, genetic cluster in population, and that's the beta for the marker. Of course, the p-value is just based on the genetic part, so just on the markers or on the significance of this coefficient. Yeah. So I'm plotting this one, so this way better. You can see that the inflation is corrected already quite a lot. And the other example we would see is now a correction using not the membership to the clusters, to the genetic cluster, but the principal, in this case, the principal coordinates. So with the arguments Q true and QBCO is the number of coordinates that you want to include in the model. So in this case, we will just include the first and the second principal coordinates as fixed effects in the model. And you can see also that based on the inputs, yeah, it's a the software see whether you are providing haplotypes or or SNPs. And this is also done. So let's have a look at the betas now. So now we have, still the intercepts. Then those are the two principal coordinates that we included, and those are the genetic effects of all the alleles of this locus. I'll plot it as well. Okay, just so for the visualization, there's also this function that can be used to compare the sky plots. So in this case, comparing the one in which we corrected just with the membership with the one in which we have corrected with the two principal components. It's taking a little bit more for plotting. This is now overlapping some points here, so that's why there is some transparency also in the points. So that's why it's taking a little bit more. And we do not have the axis yet. It's also my computer a little bit slow, I would say. The axis will come, but just to show you that, this is just a function to plot together, say, two sets of p-values and compare them. Yeah, well, axes are not coming, but let's go for the next one. Believe me, they should be there. Okay, so the other example I want to run is actually now the correction of population structure that is based on the kinship matrix. So the calculation is within so you see the axes are there. The calculation is of the matrix is still within the map.qtl function, although you can also use this function and do that beforehand. For example, if you want to calculate a matrix and then provide that matrix, that's also possible. Okay, so in this case, we are using this bilateral SNPs. We are correcting by the kinship. This argument is just an argument to sample the SNPs for the kinship matrix calculation in case you don't want to use all of them, but just an equally spaced set of markers. Could be useful if you have many gaps, for example, in the map. So you just provide the sides for a bin, and that's in the unit, in the map unit that you have provided. So since this map is in centimorgan, this is every centimorgan. If we'll sample one marker every centimorgan. Now it's actually running a mixed model. because we are providing a kinship matrix to the random part of the model. Perhaps it will take a little bit more. I'm sorry you couldn't run it. Actually, I didn't realize that the material was not coming through the email. Sorry for that, but perhaps you can do that later on. I will try to solve it with Delany. So we are almost at the end of the workshop, so we are still on time. Exactly. Now this is taking indeed a little bit more time. That's because it's a mixed model. So now it's okay. In fact, is doing a parallelization over markers. So for each phenotype, each marker is an independent association. So then, if you have more cores in your computer, you can parallelize over the markers. And this is somewhat different. So the output, in fact, here we have we have still the beta, the results of the F-test. We have the residuals as well, the p-value, just for the genetic part, so just for the markers, and standard error. And then we have also actually a valve test, which is pretty similar to the F-test. But what I wanted to show, well, this is the sky plot. What I wanted to show is the betas here. Again, we have just an intercept and the coefficient of the marker that we used. In this case, we used the SNP, a SNP dataset, so we have just one coefficient. Okay. So a few other things. I mentioned that you can add covariates or cofactors to the model, and then can be done. That can be done by these arguments. So here you can provide a cofactor or a covariate actually, and here you can specify indeed whether it's categorical or continuous. So in this case, we are it's just a fake example, but we are using a cofactor. So we divided the individuals into some groups. This could be, I don't know, different locations, for example. For sometimes it's convenient to have this cofactor included in the association model, so that is jointly accounted here. Otherwise, you could also do that in advance. So I'll run this one as well. And then we will have just a few comparisons in the end and something about visualization that we are about the end of the demonstration. So this is again taking some time. In the meantime, I can start explaining a little bit about then. So after you run the association, you want to also calculate significant threshold for the association, and that's because we have the problem of the multiple testing. So there are actually two approaches that can be used in the package. One is just using a permutation over the whole population, and so you can define the number of permutation and the level of significance. So that's one approach, and then the approach that you can use for haplotypes. Then only for when you have biallelic SNPs, you can also use this other approach. Is the method developed by Lee and G. It's actually a kind of Bonferroni correction, but is dividing by the effective number of tests. So it's first using a multivariate approach to identify the effective number of tests. So a number, let's say, of independent markers, I would say. And then it's using that number to the in the Bonferroni-like correction. So it's known to be less stringent than Bonferroni. Okay, so this is the association is done. So I will put here the p-values, and this will be a comparison plot again, where we have a little bit bigger. We have the comparison of the analysis with the cofactor in the model, which is the pink here, and the green with no cofactors. So I will run the permutation. The number of permutation is very low just here, just because of time. Of course, you usually want to have a high number to be more accurate. So we run these two methods for the significance threshold, and we will compare them in a plot. And then I will show you just the last plot to conclude.
We have 5 minutes to finish up, Giorgio.
Yeah, thank you. I think we are at the end. Yes. So this is the permutation result. So it's basically the same result as before. There is an additional element, which is the permutation threshold for each phenotype, and then we will run also the Lee and G approach, in which So here you can see that you have for each chromosome this number, which is the number of effective number of tests. The effective number of tests, and this is the result. So you have the threshold there and the number of tests. So in our scale, this will be the threshold. Of course, this approach is not. It's just based on the genotype, so it's not It's not per phenotype like the permutation. So I will just plot here the permutation threshold. And the last thing that I want to show you is another visualization of the association between the phenotype and the genotype to a box plot, actually. Pretty simple. Now I will take the best marker for some of the analysis we have run before. This is a SNP for the mixed models with the SNP. This is the best ample type, ample block. And here I will list them. And so this is the function to run this kind of plot. You have to specify the phenotype and the marker. It's easier if I just show you. So basically, it's a simple box plot. It can be used just for discrete genotype data to visualize the association between the phenotype and the dosages. So now this is an example of a biallelic SNP, but then the function can be used also for the haplotypes, in which each here for each haplotype you have the dosages that are occurring in the population. So it's not very easy. Now we have quite a in this example quite a number of haplotypes. It could be quite difficult to read it. In fact, you can focus, for example, in the haplotypes in which you see the variation, or which is like this one. So you can select the haplotypes in which you see the variation and plot only them, and it's in this case easier to see them. That's it, basically. This is what I wanted to show you. It's just to illustrate some functionalities, but sorry for that. It was not ideal that you couldn't run it. So I hope it was clear, at least.